So this video is going to go through some common errors that students make when it comes to acid-base reactions in organic chemistry. So the first one is treating sodium hydride like an acid or breaking carbon oxygen bonds into the ionic pairs. So let's start off with the sodium hydride. So an example of this would be something like this, where you're given a reaction between sodium hydride, between something like an amine, and told to predict the products. And so what students often do is that they see that there's a hydrogen right here, and they think, oh, like we can protonate something. And so they'll draw the arrow from the nitrogen to the hydrogen and give that electron pair to the sodium. And the products that they get look like this, where that sodium has a lone pair, and we get an H3 here. And so the problem with this is that we end up having this negative charge on the sodium. And we know that sodium really does not want to have that negative charge. And so this equilibrium will never form. And so we never want to treat sodium hydride like an acid. It's always going to be a base within the reactions that we do. And so the correct way would be to have the sodium hydride treated like a base, meaning that we split up that sodium into the sodium positive and the hydrogen with the minus charge, meaning that that hydrogen has a lone pair of electrons. And we instead start the arrow at the lone pair, draw it to the other hydrogen on the other molecule, and then break that nitrogen-hydrogen bond. And so the products of this reaction should look something like this, where we have that cation pair for the sodium as Na+. We formed a new hydrogen-hydrogen bond, so we'll get H2. And then we lost a hydrogen bond to that nitrogen and ended up with a lone pair on that nitrogen. And so this would be the correct reaction or products for this reaction. And again, that's because we're treating the sodium hydride like a base. And that hydrogen actually is the one that has the lone pair that attacks another hydrogen and forms H2. All right, the next type of error that I see, and it's kind of related to cation anion pairs, is when people see a reagent like this, and they see that, oh, we have this OH here, and similar to general chemistry, we can rewrite this as having that negative charge right here, or sorry, a positive charge right there, as having this, and a negative charge as this. We cannot do this because we cannot break a covalent bond. This carbon-oxygen bond that existed is covalent. We can't just break it apart similar to like the ionic bonds that we broke apart in Gen Chem between sodium and OH. And so we cannot separate these out like this. This cannot be done. You have to keep that initial reagent whole. And so to avoid this mistake, just don't redraw them as that positive and negative charge. Only do that if you have a sodium, lithium, or like one of those metals from the first or second column. All right. The next common error is confusing stability with strength. So in the previous video, we talked a lot about equilibrium and about what it means to have a weaker, stronger acid. And so a lot of times what I found is that students sometimes confuse stability with strength. They are not the same thing. An acid that is strong wants to react. And that means it is less stable. It doesn't want to exist in the same state. It wants to transform into something else. It wants to react. And so that means a weak acid is more stable. And it does not want to react. All right. Okay, the next one is treating a positively charged species as a base. So sometimes this error, I see this error the most common, usually with nitrogens. So something like this. If somebody has an amine right here, and they have, let's say they have this compound here, they will treat this nitrogen like a base. And I think this error occurs because nitrogens often are bases and they often have that lone pair of electrons. However, in this case, this does not have a lone pair. And so if we were to draw this out as like to show like all the bonds, we would get something like this, where we have that nitrogen, and we can see that that octet is entirely comprised of bonds and no lone pairs. And so what that means is that there are no lone pairs, which means cannot react as base. And so again, in general, if you see a positive charge, avoid treating that compound like a base. You should instead be thinking about it being an acid and looking for which hydrogens are able to be pulled off. All right, the next common one is deprotonate the wrong H. So for this, it usually occurs when you have like a more complex structure. So let's just draw out a more complicated molecule. I'm just kind of arbitrarily drawing something out here. So let's say that we have something like this. And so we can see that we have a lot of different options here. We have a lot of hydrogens on this molecule. And one of the most obvious hydrogens is this one right here. However, we actually have a lot of other hydrogens here that can also be deprotonated. So we can see that we have hydrogens right here. We have some hydrogens right here. I'm not going to draw out every single hydrogen here, but we have hydrogens that are on the ring. And then we have like those alkane ones in the middle, which are a little bit less interesting because we know that those are not really acidic. And so if we look at the pKa values of these different functional groups, we can determine which one would actually be deprotonated. And again, for this, you'll need a pKa table, but you should just, in general, you should have a general sense of which kind of functional groups are acidic. And so these red ones have a pKa of around 40, so they're not very acidic at all. This purple ones right here next to the ketone have a pKa of around 18. The blue ones have a pKa of around 20. And then this NH2 has a pKa of around 40. And so despite those hydrogens on the nitrogen being the only ones that are drawn in within like a normal skeletal structure, they're actually not the most acidic because they have that higher pKa. And so what we see is that in this structure, those purple ones are actually going to be the ones that are more likely to be deprotonated because they're more acidic. And we could also draw out the conjugate bases and show that the negative charges that form when we deprotonate those purple ones will end up being resonance stabilized. And so if we were to draw a reaction between this molecule and something else, we have to make sure that we deprotonate the correct hydrogens. And so the products that we should get between this and a base should involve deprotonating these hydrogens right here. So I'll draw that out here. We have this deprotonation here, arrow goes here, and we end up with this product. And then that nitrogen-hydrogen bond doesn't end up getting touched here. And so again, it's really, really important to not accidentally omit hydrogens that are less obvious in your when you're trying to decide which hydrogens would actually react. All right. The next one is confusing the element effect with the inductive effect or forgetting resonance rules. So I'll show kind of a few different examples of this. So the first one is something like this. Where let's say that we have this acid versus this one. One error that I've noticed is that students will say that the structure on the right is more acidic because of the element effect, because they notice that there's a fluorine here versus a chlorine. However, the structure on the right is more acidic because of the inductive effect. And that's because the hydrogen isn't directly bonded to the fluorine. We only use the element effect to compare structures where the hydrogen is bonded to different atoms. And so the usually with this, you get the right answer. You say which one's the correct or more acidic, but then your reasoning might just be not quite right. All right, the next one is some resonance rules. So for example, let's say that we have this structure here. Versus this structure. And so sometimes students will say that this structure right here is more acidic because of resonance. And the reason they say that is because they see that there's two double bonds that could potentially engage in resonance once the hydrogen is deprotonated. However, in this case, while it's true that two double bonds is generally better for resonance than one, and it stabilizes charges more, this doesn't quite work in this case because those double bonds are too far away. And so these double bonds cannot participate in resonance with that oxygen. Because if you have this structure right here, where you have that negative charge on this oxygen, you're interrupted by this carbon right here. Because this carbon breaks the link between the oxygen and the double bond. There's no way to get those electrons to flow through that carbon. And that's because that carbon is sp3 hybridized. However, on the structure on the right, we can see that if we deprotonate the oxygen, we don't interrupt the system. It's all linked. And so this one is resonance stabilized, where the conjugate base would be resonance stabilized. And it's close enough to participate in resonance. And so since it's resonance stabilized, it's going to be more stable, which means that the initial acid was more acidic or stronger acid. And so again, it can be sometimes misleading if you have those like multiple double bonds that are further away and it looks like it could potentially participate in resonance. However, in this case, it cannot. All right. I think some other common examples of common mistakes are shown in those practice problems. So again, I recommend going through those if you haven't done so already.